we will start our second keynote talk today. We are very delighted to have our second keynote talk given by Professor Ronghui Liu from University of Leeds. She will introduce the insights on applying the AI and data science to multimodal transport. Welcome.
Thank you, Professor Gao. And thank you, Professor Liu, for can you hear me? Right. So thank you for the organizer for inviting me to come to speak in this audience. AI experts here, which I'm not. But I hope I will use this 30 minutes or so to present you some of the challenges. I'm from transport studies field. Some of the challenges we face in transport, and also give you, as earlier speaker Anna introduced, some of the background and the problem we have. And really what I like to get from here is some interest in solving transport problems. And I heard earlier call from Professor Liu about data sharing, etc. We do have a lot of data. It is how to process that, how to use that, and how to analyze this to address the questions we face. So I very well welcome anybody after talk to come talk to me or email me afterwards. So, as Professor Gao introduced, I'm Ronghui Liu. I'm Director of Research at the Institute for Transport Studies at the University of Leeds. We call ourselves ITS Leeds, and in transport field, we are the largest in the UK, have some 90 staff members, 80 PhD students, and over 100 master students. We don't, in this country, in transport, we don't have a transport undergraduate. So our cohort starts from master's level. So as I said, today I'd like to explore with you more on how AI and data science can and are indeed shaping transport systems into a more intelligent, efficient, and equitable mobility systems. Do I just? Oh, right. Okay, thank you. Right. Okay, so I will begin to lay out some of the context of AI and data science in transportation. So transport system is really a complex and dynamic system. I think even though you're not maybe not working in the field, but we all experience transport in our daily lives. And it's really a complex dynamic system that evolves, involving the movements of people and the goods across networks. And these movements are influenced by our demand for travel, by the infrastructure available, and also the environment, for example, the weather conditions, that are very much also by the policy implemented into our system. But after all, it's involving and influenced by our own individual human behavior. And as the city grows, such mobility activity patterns become even more complex, and this complexity making the traditional transport planning increasingly difficult and can't keep up with the evolving in mobility trends. Now, with the explosion of data, I mentioned that in our field, the data it's not a problem. We have too much data, if anything. So with the explosion of data available to transport professions, such as vehicle trajectory data from GPS and various sensors, you may or may not know, along all the motorways in the country, every 500 meter and every lane, there is something we call the loop detector. It's basically can detect a passing vehicle, so it gives us the speed vehicle and number of vehicle and the type of vehicle passing. And that's just one of the examples. So all the motorway and many of the A roads have such instrumented sensors installed. So we have explosion of data from GPS, from various surveillance sensors, smart cards we use every day, social media, and mobile apps. This really gave us an unprecedented opportunity for the transport profession to try to understand and optimize our transport system, and in real time. And that's where we see such multimodal AI can provide powerful tools for us to interpret it, to help us interpret and analyze and simulate and predict and movement patterns across different networks. And by combining data from these different sources, it can help us to create a smarter, a more adaptable and responsive and more user-centric transport system, and also help leading to better planning in such increasing complex mobility patterns. Look at the data available. Transport AIs really thrives if we develop transport AIs. They really thrive on the multitudes of data available to us, as I mentioned, from video surveillance that can detect a vehicle and road activities, to GPS trackings of trajectories and predicting movements of movement patterns, to mobile phone and social media to capture real-time user feedbacks and crowd dynamics, and to ticketing system that help us to reveal the demand and the usage trend, as well as to sensors on our infrastructure, which give us a more comprehensive real-time knowledge of the status of our infrastructure. And together, these diverse data sources can help us create a comprehensive and real-time picture of how people and goods moves, and therefore enable the goal our transport profession wants, which is a smarter decision, making dynamic decision in real time, and making our planning more adaptive to changing mobility systems. So let me perhaps walk you through with one example. That's an example of using sensor data, raw sensor data, to help inform high-level decision makings. In this case, I'd like to take the example of dynamic pricing used by many Uber-type rider-hailing companies. Dynamic pricing means that for making the same journey, you can be charged a different amount, depends on the level of congestion and the level of demand for that service. So ride-hailing companies do so by integrating advanced technologies such as cloud computing, Internet of Things, mobile apps, and blockchain. And integrate such technology and with the help of AI to optimize their operations. For example, they use cloud services such as Amazon Web Service, Microsoft Azure, Google Cloud to collect, host, store, and process the large data. And then they apply AI-based analytics to process such ride patterns and to predict demand trends in real time to adjust the pricing. And as well as dynamic pricing, there are a range of other options, functions they use AI for, dynamic route optimization, AI-driven navigation, routing for drivers to minimize delays and fuel consumption based on current and predicted traffic congestion, and then AI-powered customer support, AI chatbots assist riders and drivers by answering their common questions, but also providing more optimized routing. So that was one example. But coming back to transport system again. So transport, like any other system, has two parts, a supply and a demand. Transport supply refers to include, for example, the infrastructures, the vehicles that move people, but also the level of service, the frequency, the capacity, the routes, and available modes of transport. So altogether, we call it part of a supply side. And I can see that in this space, AI can really help tackle the challenges we have, such as analyze from fragmented data across different providers, for example, from private taxis, from public buses, and can also help to for real-time optimization under uncertainties, for example, under different weather conditions or events, large events, and also help us aim to achieve sustainability goals as well. And the AI can help us do so by integrating such diverse data sources I mentioned earlier, and to create a more coordinated and efficient transport supply system. As well as the supply, so we have also the transport demand. So transport demand is a broad term describing the needs or the desire for movements. Where we want to, how many people want to travel, where we want to go, when we want to go it, and in what way we travel. So mobility demand can vary by time of day, location, but also by socio-economic background of the travelers. Now, in this space, you can tell me more, but from my perspective, I can see that AI enable us a much deeper understanding of the diverse traveler needs by inferring from the large data the preferences and the routines and the routes people make for their daily travel. And such analysis can support very much on our mind was to develop equity-aware modeling to account for marginalized users, for example, disabled cohorts, low-income travelers, and enable much fine-grained demand prediction, such as looking at the last-mile travel, micro-mobility needs, and at a higher spatial temporal resolution. So demand and the supply are not a one-way route, are not separate. They are highly evolving with each other and continually shape each other, and in such a way which are often very complex, dynamic, and frankly, for us, it's really hard to predict. And this is where I can also see that the demand-supply interaction is another area where multimodal AI can really assist. And they can help us to really close this feedback loop between the supply, the infrastructure side, and the individual experience. And fusing from the range of data sources I mentioned, from vehicles, GPS, sensors, smartphone, apps, etc., fused with AI technology allows us to monitor how people make their daily mobility travel, and in a real-time case. At the same time, when we design the supply, design our network infrastructure, how we build it, where, what we build, what kind of infrastructure we build, where we subsidize, provide subsidy, and what we prioritize. Now we prioritize public transport, prioritize micro-mobility, etc. All these supply interventions can also shape demand, can also alter and influence our demand. And then AI and AI-enabled simulation technology and digital twins can help us to simulate and learn from this interaction before we actually put that into practice. Take one example of such demand-supply interactions is the differential transport policy. That is really to design, to segment travelers based on their behavior and needs, and to implement more targeted strategies. For example, time-based fare. So during the peak, it may charge more, so peak spreading, so flatter the rush hour congestion a little bit. And the targeted subsidy, for example, target to low-income groups and certain high-demand groups. And increasingly, in addition to what we are known accustomed to those fixed bus routes, we could provide more flexible bus routing based on the demand and into certain unserviced area using real-time demand data aggregated from multiple sources. All these kinds of differential policy, transport policies, are very much in the mind of transport professions and been developed not just academics, policymakers as well, but with our traditional methods, which I won't go in details here, it's really difficult for us to evaluate their potential benefit. And this is also where I can see that AI and multimodal AI can be a powerful tool for us. I mentioned that many of this policy needs to be simulated, and the digital AI-enabled digital twin is another big research interest in transport too. Do I have a few more minutes? Right, okay. With a few more minutes, I'd like to perhaps work through, although we are coming from transport side and not AI specialist, but AI has been in at least the last 10 years going in strongly into the different domains of transport. And with a few minutes, I'd just like to talk you through one or two examples that we have worked on from an EU project.
Can we just clarify, you are 20 minutes into your slot, you still have half of the thought.
Oh, right. Okay, right.
20 minutes.
Right, okay.
Q&A, yeah.
All right. Okay. Thank you. So this is a EU-funded project called Roadmap for AI Integration in the Rail Sector. So very much they want to look at developing roadmaps and looking at where AI can be applied in the railway domain. So I want to, so the project just finished here. Interested can have a look on the web page, and broadly we map out all the various railway domains, covering safety, security, railway maintenance, inspection, automation, driving controls, traffic management, passenger mobility, policy, and resource management, except the policy and resource management, which we thought maybe at this stage less relevant to AI. All the other areas have a strong capability and the needs for AI implementation, and we did do a systematic literature review of the relevant studies in the AI and the rail domain, and I think the paper was. Yes, the paper was published in Transportation Research Part C. I think if you look up, it's still one of the most downloaded paper on this journal. Among those, the project actually focused on 3 main areas. One, AI for automation and train control, AI for predictive maintenance and defect detection, and AI for traffic management. I think I will just talk about the first one, AI for automation and train control today. But firstly, I give a few definitions. By automation, what I mean here is the ability of a system to automatically or semi-automatically, that means with or without human intervention, or with only partial human intervention to perform a certain task, like driving a train. Autonomy means the ability of system to dynamically adapt to unexpected scenarios by taking independent decisions. In both of these, we can see the role of AI there to make vehicles in the railway sector, trains, for example, capable of learning from experience and take autonomous decisions to adapt to changes in the environment. So the table, I don't know whether you can read on the left there, is industry standard definition of a grade of automation in the rail industry. So grade of automation 0 is that the train operations are done completely manually, supervised by the driver with no automation at all. Level 1 is that the trains are manually supervised by driver, supported by some form of automation, something called automatic train protection. This is a system implemented on the train, on all trains, which can automatically detect a certain danger scenario and then basically just pull the plug, stop the train. So if you ever experience a sudden stop of train, most likely it's ATP plays the role there. Grade 2, grade of automation level 2 is a semi-automatic train operations through something called automatic train operation, ATO, and ATP, to automatically manage the train operation and protection and supervised by driver. This is in fact most of what, if you traveling on London Underground, most of our London Underground system are at level 2. There are drivers at the driver's seat, but the role of the driver is really when the train needs to leave, just press a button and train will drive itself to the next next station, and driver will also control a door opening and closing. So that's level 2. Level 3 is driverless train operation, but still with onboard staff to handle emergency situations. Whereas at the ultimate level 4 is you don't have any staff on board, everything, but there are still centrally controlled systems here. So although in the current system here, this level of grade of automation only really consider automation, but not as much of autonomy. In the project, we look at how we can move from automation to autonomy. And the picture on the right-hand side is an illustration of how such system can be developed based on some of the existing facility in the railway domain. So we already have the automatic train protection system, and that can be further developed for it to learn from unseen and making a decision. Rather, currently it's very much rule-based. It can be further developed as a more intelligent system. And then in the middle layer, intelligent train operation built on the current automatic train operations to have more intelligent train operations with the functions, for example, including, for example, energy optimization, so how to control the train speed, taking into account of the changing the track geometry, gradients, curvature, etc., to optimize the traction, to optimize the train driving speed, therefore to minimize the traction energy consumption, to capacity optimization, as well as comfort. And then moving from automatic train protection down to more intelligent train protection, that's where they can automatically, using AI, imaging, processing, and learning, to automatically detect obstacles on the track, and then enable automatic train protection to take place. While implement this, we also look at the grades of intelligence. So from grade intelligence level 1, we're looking at with limited or no autonomy. But here, AI is used for non-safety critical functions, such as automatic train control, speed control, automatic braking, etc., and also in real-time communication. Moving to level 2, again, needs with the partial autonomy in an open environment. Here, AI can enhance the automatic train operations and automatic train protection with more intelligent offerings, which can read and interpret complex scenarios. To level 3, with the full autonomy in an open environment. And here, both intelligent train operations and the intelligent train protections. So not just based on rules, but be able to learn and adapt and detect obstacles to act. To level 4, a full autonomy in a fully connected environment. So if I say up to level 3, we'll consider maybe just one train, how to make that train, operation of that train more intelligent. To level 4 is to operate a network of trains. So this way it can mean, for example, to better manage the delay in case one train is delayed, how to manage it, to allow which train to go ahead, etc. So that's what we consider as level 4. And again, all this will be leveraged by technology, using cloud computing to store large data for sharing and exploration and fog and edge to monitor and manage the interaction of assets and to allow onboard system to make more localized and autonomous decisions. So I mentioned earlier about the digital twins here, and that's increasingly is an area of development. And I take here an example of developing digital twins for railway assets. And digital twin for railway assets essentially is a digital representation of the physical assets, railway asset systems. And with such a system, hopefully help us to perform analytics. And the digital twin system has already been developed over the years. And in our project, we look at how AI can aid on the digital twin development here. On the one hand, we think digital twin can help produce. Early on, I talked to during the coffee break, talking about some domains have less data. In fact, although I said in transport we do have lots of data, but certain safety critical scenarios are few, and thankfully they are few. But digital twin, for example, can produce such kinds of scenarios for us, whereas AI then help us making more intelligent, adaptable decisions with that. Okay, with 5 minutes left, I will perhaps quickly go through some of the developments currently being made in my field of transport. So AI for general transportation. In the domain of transport, AI with contextual understanding and reasoning currently plays a critical role in interpreting the complex and dynamic traffic scenarios here, especially those involving ambiguous multi-agent and unusual conditions. And in modern transport system, AI excels at handling massive data from diverse data sources, as I mentioned earlier, and enable dynamic decision makings. Intervene as well. AI has also generally been used in creating autonomous driving conditions by generating diverse scenarios for us to create such scenario libraries and leverage large functional models to enable robust end-to-end learning. And this approach enhances the system's ability to interpret, adapt, and safely operate across a range of complex scenarios. Visualization is being used, increasingly used across all modes of transport. Here, AI enables the integration of large spatial and temporal data from, in this case, from residential or workplace zones to construct detailed commuting networks and use that to analyze the travel diversity and behavior. I mentioned earlier about agent-based simulation, decision-making as well. AI here plays a vital role in traffic situation awareness and decision-making analysis by enable a comprehensive real-time overview of the urban road networks and help us conduct congestion analysis and deliver real-time traffic condition on the road to inform and enhance day-to-day traffic management. And here also being used as a detailed lane-based navigation services here, and traffic flow predictions, again, gathering from all kinds of data sources to give us real-time information on the traffic condition on the roads. But roads and the rail aside, increasingly, especially low altitude urban air mobility is a fast developing area. We just submitted a proposal to EU European funding body. We thought it might be just a handful, but it turned out there were 36 submissions for one project. But this is a large area, fast developing area in transport. And then here, there are vast opportunities for AI that can accelerate autonomous driving and low altitude planning management, again, by integrating multiple data sources from air, space, as well as ground to integrate more comprehensive air-ground design and digital controls. So I finish here by perhaps echoing something Professor Liu said earlier for inviting interdisciplinary collaborations, and come back to what I started. What I'm here is really hopefully gave you some flavor of the kinds of challenges we have in transport, and really hoping we form collaborations, and hopefully we can form a few collaborations after my talk. Thank you very much.
Thank you very much, Professor Liu, for the excellent talk with full of insights. Now we have a quick question. One question.
Oh, I'll stand up. Thank you so much for the fascinating talk. I really like the work with autonomous railway and at the last low altitude air travel. So my question is related to the autonomous nature of the transport and related to the reasonable intelligence. These models are responsible to make the transport autonomous. So would you like to put some highlight on the research that is related to the safety of these models, or maybe the confidence on these models? And the second question is, would you see in near future about the safety of these models can be combined with the research of digital twin? Thank you.
Thank you very much. It's a great question, but it's also a big question. Such models are increasing. The AI-driven models at a different level of intelligence are being applied in various transport domains. For example, in providing better knowledge of situation awareness, that's very much in there. I mentioned earlier, Uber-type companies are using it for dynamic pricing. Back to the railway domain here, I mentioned about intelligent train operations that I understand is already in there, both driving the trains, but very much in obstacle detection and assisted train operating automatically, but also that's a safety critical element. Even in less safety critical element, for example, just how drive the trains more intelligently, for example, making them more comfortable or reduce energy consumptions, for example. And there are already AI-enabled algorithms there for the trains to best. I mentioned that most of trains are London Underground is at a grade of automation level 2. There is a driver, but driver doesn't drive the train. It just press a button. What that button does was because there are already internally have done a calculation of the speed to drive to the next station, for example. But the system don't always follow exactly what that one. And there are lots of adjustments happening there, and AI is playing a role in there already. As is mentioned, there's a big question, and I can follow up, give you a bit more examples if you like.
Thank you very much, Professor Liu. If you have more questions, you are more than welcome to talk to Professor Liu in the lunchtime. Let's thank you, Professor Liu again.